In this experiment, we will be determining the composition of limestone. In this first week, we'll be working with highly concentrated chemicals, so it's important that you pay close attention to your TA when they go over laboratory safety procedures. This is the start of needing the laboratory safety mindset that we've been building this semester will really come into play. In this lab, we're going to examine the composition of limestone. We will determine what the mass composition is of the anion and the cation comprising limestone. We are also going to focus on stoichiometry. We will talk about percent composition and learn some new laboratory techniques. A full list of objectives for the lab are available on the course Canvas site. Limestone is an extremely common sedimentary rock that comprises most of the exposed rock on Earth's surface. From a chemical standpoint, limestone is composed of the minerals calcite or calcium carbonate, chert, known as silica or SiO2, and dolomite, a calcium magnesium carbonate. In this lab, we are going to determine the percent composition of the calcium carbonate in the limestone sample. To do this, we are going to first determine the amount of anion or carbonate in the sample by reacting the limestone with hydrochloric acid. Then we're going to react the remaining sample with another substance to determine the amount of the calcium ion present. Chemists often want to know how much of a part is present in a whole sample. This is called percent composition. Percent composition is the percent by mass of each element in a compound. To find the percent composition of a part of a compound, you take the mass of the part and divide it by the mass of the whole compound, and then multiply it by 100%, keeping in mind that for a compound, we're interested in the mass of an element in 1 mole of the compound. Let's look at an example. What is the percent composition of nitrogen in urea? We first have to find the molecular weight of urea. We know that carbon's molecular weight is 12.01 grams per mole. Oxygen's is 15.999 or 16 grams per mole. Hydrogen's is around 1.01 grams per mole. And nitrogen's is around 14 grams per mole. We need to add all of these together with respect to their stoichiometric amounts. So if we look up our chemical formula, we see that we have 1 carbon atom, 1 oxygen atom. We see that we have 1 nitrogen atom, but it is multiplied by 2, so there's 2 of them. So we'll multiply by 2. Hydrogen, there's 2 hydrogen atoms, so again we have this multiplier, so we're going to make that multiply by 4. And so now all we need to do is add these up. And we'll find that urea has a molecular weight of 60.04 grams per mole. Now we need to determine how much of this is due to nitrogen. To do this, we take nitrogen's molecular weight, 14.00 grams per mole, and we see how much nitrogen is in 1 mole of urea. So if we look back again up at our chemical formula, we see that there are 2 nitrogens, so we're going to need to multiply our 14 times 2, and then we're going to divide that by the molar mass of urea, 60.04 grams per mole, and then multiply by 100%. When we do this, we find that our percent composition due to nitrogen in urea is 46.6%. So how are we going to determine the percent composition of the anion and the cation? Well, we will isolate them, starting with the anion carbonate. Calcium carbonate reacts with hydrochloric acid, releasing carbonic acid into solution. The carbonic acid rapidly decomposes into water and releases carbon dioxide gas. We can see the gas released in the form of bubbles in the solution. This two-step process occurs rapidly and is generally described using the net reaction. Calcium carbonate reacts with 2 moles of hydrochloric acid solution to form aqueous calcium chloride, carbon dioxide gas, and water. We can measure the amount of the calcium carbonate limestone sample and the amount of hydrochloric acid that we start with, and we can measure the mass of any kind of remaining solution. That's going to be what contains the calcium chloride and the water. Any mass difference there would be due to the release of carbon dioxide gas. So working backward through the stoichiometry, we can determine the amount of carbonate present in our original sample. This leaves us with determining how much cation is present in the sample. If we follow through our previous reactions, we've released carbon dioxide gas into the air, and our sample is left with the calcium containing calcium chloride and the water. We can further react our solution with another substance, ammonium sulfate, to form solid calcium sulfate in basic conditions. This means the pH of the solution must be between 7 and 14 pH units. As calcium sulfate is a solid in basic aqueous conditions and the other product, ammonium chloride, remains dissolved, we can filter the solid out of the solution in order to dry and then determine its weight. Ammonium sulfate is a substance known as a precipitating agent, meaning it selectively combines with the element of interest to form an insoluble solid in solution. Chemists can isolate the precipitate using gravimetric analysis to determine how much of the precipitate is present. In order to isolate the cation from limestone, you will need to filter any undissolved solids from the anion portion of the experiment. In the experiment, you will utilize two types of filtrations: gravimetric and vacuum filtration. Gravimetric filtration simply uses gravity to push liquid through a filter paper. Often, the filter paper is folded up and put into a funnel so the liquid can be collected separately of the solid. The second method is vacuum filtration. Like the name implies, we will use a vacuum to suck the air out and our liquid through the filter paper. And we will use a specialized funnel known as a Buchner funnel to collect our sample before it is run into the vacuum flask. The vacuum flask has a special sidearm attached to it so that it can be attached to a vacuum source. This lab will also be your first time working with pH and indicators. pH measures how acidic or basic a solution is. A pH greater than 7 means that the solution is basic. A pH less than 7 indicates that the solution is acidic. Indicators change colors based on pH, providing a visual indication of pH change. Carefully read through the procedure to identify the indicator we will use in this experiment and the color it starts out as and changes to, keeping in mind that you may see 3 different colors as the pH changes. A few reminders for this experiment. Record actual volumes used for all liquids. You should always estimate 1 decimal place beyond the markings on the glassware. So for example, if you're using a 10 milliliter graduated cylinder, you should always estimate between the markings. If we look at some graduated portion of that graduated cylinder blown up, you can see that there is space in between the lines. So the whole numbers are marked off when we know that we've got at least some volume between 1, and you can see in between the lines are marked off to the tenths place, so you can estimate 1 additional digit. Okay, so you got to remember, if you're using the 10 milliliter graduated cylinders with markings to the 1/10 mark, you can actually get 2 decimal places because you can estimate the difference of the volume level between the 2 markings on the glassware. It's important that you record the actual volumes and masses used. The values listed in the lab manual are approximate and should be used as a guide. As a scientist, you need to get in the practice of recording what you actually use, not what is just listed in the lab manual. This makes your measurements more accurate, which means the results of your calculations will be more reflective of the original sample that you used. Use distilled water to avoid introducing additional impurities into your reaction. Please make sure that you follow your TA's directions on using the DI water tap and that you carefully push the handle downward when attempting to get the water on. Also, the DI water tap is regulated, so please do not force the handle while trying to increase the rate of the water flowing out. You won't get more water flowing out. You will also need to record the mass of the filter paper in the watch glass so that when you weigh the filter paper in the watch glass with your sample, you can subtract out those 2 values so that you know what the mass of your sample was. Make sure that you let your sample dry completely in the oven before you take the mass of it. If your sample is wet, it will be heavier than you expect and will result in your ending mass being greater than your starting mass, which is not physically possible. It also makes it more challenging to write your lab report, as you'll need to explain this in the future. Most importantly, we will be conducting this experiment on 2 different limestone samples to see how they compare. Because of the length of the experiment, you will need to test both samples at the same time. You cannot complete the lab with one sample and then go back and complete it with the second sample. There simply is not enough time. This experiment is the first experiment where we will be using hazardous chemicals. These substances must be disposed of in a particular manner following local and federal regulations. Your TA will instruct you on the specifics of waste disposal during each lab period. For the general chemistry labs, we mostly use acids and bases in aqueous solutions, so we generally refer to the aqueous waste containers as simply the waste container. Other labs will have to separate out other types of waste into separate waste containers, so please pay attention to your instructors on how they want you to dispose of waste. For this lab, make sure you put the waste in the appropriate container. All acids go in the aqueous waste container, as does the aqueous ammonia and ammonium sulfate. Leftover methyl red indicator can also go in the waste container. And the solid waste of leftover limestone or other solids can go in the trash can. When pouring waste in the waste containers in the hood, please double check before you pour your waste into the waste container that the funnel is open or in the up position, as shown in the picture on the right, and not closed, as shown in the picture on the left. When multiple students pour waste in a closed lid of the funnel, it becomes not only a safety hazard for others in the lab, but also a serious safety hazard which has resulted in injury of our personnel who prepare your labs. A last couple of hints for you. First, come prepared, meaning read the procedure in the lab manual before you come to lab. It will often take you 2 or 3 read-throughs to understand what you will be doing. Then, write your procedure in your lab notebook. You're not permitted to have the lab manual printed out with you in lab, so having this ready is essential. You will want to identify what measurements you will need to take so you have space for them already indicated in your lab notebook. Make a timeline. This is a long lab experiment, so it's essential that you have an idea of how long it will take for you to perform each step, keeping in mind some steps require a bit of a waiting period. This also helps you figure out which steps and where you can multitask. Do you have to wait for a solution to react? Well, then go ahead and measure out some of the substances you'll need in the next couple steps. Are you going to need to record a mass too? So maybe while you're waiting, you should go ahead and weigh out the watch glass and the filter paper. Is there some kind of glassware that you can clean so you're ready to leave the lab on time while your sample's in the oven? Identify those types of steps so that you can use your time efficiently and successfully. And when in doubt, speak with the TA in the Learning Center or ask the lab supervisor if you have questions about the procedure you're performing in the lab. Remember, if you have any questions, ask them on the Course Piazza site, reach out to your TA or myself via email or office hours to ask.